This is our first video on multi-body problems or multiple body problems. The key about multiple body problems is that the system at any given moment is what we say it is. If you look at this picture, for a certain aspect of the problem, I might say, you know what, I want the system to be the whole thing. For another aspect of the problem, to solve some other particular value that I'm asked to find about, it might be convenient for me to say, okay, now for this part of it, I'm just going to say that block 1 is the system. Or maybe blocks 1 and 2, I'm going to consider that to be the system. Or maybe just block 3 by itself. Maybe that's going to be the most convenient system for me to use in solving that aspect of the problem. The deal is, Newton's second and third laws apply to that specific system no matter what we choose as the system. And so we're going to modify the system as necessary to achieve whatever ends we're looking for. Here we have a problem. We've got an applied force of 30 on the left side here. We have no friction on the bottom. And let's first take the system to be the whole thing. Well, this system's mass then is 10 kilograms because this block has a mass of 2, this one 5, this one 3. So the whole thing is the system. In fact, if I want, I can kind of go like this and say, hey, you know what? That whole thing, 10 kilograms, that's the system. Well, then we're going to use Newton's second law on that system. And Newton's second law says that the net force is equal to the mass times the acceleration. The weight and the normal forces cancel here. There's no friction. So the net force is 30 newtons from this applied force on the left. And the mass of the system is 10 kilograms. Therefore, the acceleration of this system is 3 meters per second squared. In other words, each of these 3 blocks is accelerating at 3 meters per second squared. So I can use that 3 meters per second squared if I decide, you know what, I think I'm going to change the system. Now, whenever you have a multi-body problem, sometimes you run into internal forces versus an external force. This 30 newtons is definitely an external force, but there is an up and down force between blocks 1 and 2, and there's a side-to-side force between blocks 1 and 2. And if I say that block 1 is the system, then those two are both external forces. But if I say that blocks 1 and 2 are the system, you see, those two forces are internal to the system. This one down here on the bottom, that's an external force. You see how it's touching the outside. This one over here is touching the outside, so that one would be an external force. Of course, the 30 is an external force. But if I consider blocks 1 and 2 the system, which I might do later, then these forces are internal, and I can't concentrate on them at all. So let's say that block 3 is the system. There's block 3 right there. And it has a mass of 3 kilograms. And what we want to know is what that force is and what that force is. Well, the F with a little and symbol is just the normal force between that mass and the surface, which is equal to the weight. So that's 30 newtons. And the F with a percentage sign is the sideways force that is causing this thing to accelerate at 3 meters per second squared. Remember, just a bit ago on the previous page, we said, hey, every part of this system is accelerating at 3 meters per second squared. And therefore, this F with a percentage sign has to be the mass, 3, times the acceleration, 3, 9 newtons. How about letter D? Now, let's change the system to be blocks 1 and 2. So that's what I've circled here. And that system has a mass of 7 kilograms. And this F dollar sign, which I'm pointing to right there, and this F with a pound symbol, they cannot be considered because they are internal. So If we consider blocks 1 and 2 as the system, we cannot find those two forces. We can't do it. All right, let me scoot this up just a bit here. What's the magnitude of F ampersand? That is this one right here. Well, that's the normal force that is holding blocks 1 and 2 up, which is equal to the weight of blocks 1 and 2. Blocks 1 and 2 have a mass of 7 kilograms, so their weight is 70, right? Because G is 10. So therefore, this F with an ampersand symbol, with an at symbol, has to be 70 newtons, numerically equal to the weight of blocks 1 and 2. How about the magnitude of F dollar sign? Well, now that's this one. If I want to find F dollar sign, all right, you ready for this? I'm going to screw up the picture here. If I want that, I need to consider block 1 as the system, because F dollar sign is the normal force that is holding that up, which is equal to the weight of that little guy. Well, he's got a mass, see where I'm pointing, of 2 kilograms. And so his weight is 20. And so that internal force must be 20 newtons. How about the magnitude of F pound symbol? That's this guy right here, right there. And if I want to find him, I'm going to consider block 1 as the system. Block 1 has a mass of 2 kilograms. And how is block 1 accelerating? 3 meters per second squared. And what's the only sideways force that's acting on block 1? It's got to be this F pound, because the 30 newtons isn't acting sideways. So it's got to be the friction between those two blocks that's pushing it sideways. Therefore, 6 newtons. Takes a little practice getting used to these. We'll do a few more videos so that hopefully you'll start to get the hang of it. Now, why weren't there any horizontal forces between the surface and blocks 2 and 3? Well, that's easy, right? The floor was frictionless. It says right there, mu sub k equals 0.